Hello everyone, welcome to the 17th International Electronic Conference on Synthetic Organic Chemistry. The title of my presentation is Copper-1 Catalyzed 3+2 Cycloaddition Reaction with Mechanistic Disparity, a DFT Study. Let me introduce myself first. I am Ms. Hanusha Bakwa, an MPhil PhD scholar in the Computational Chemistry group of the University of Mauritius. I am being supervised by Professor Ramasamy and Dr. Ayman. The outline of my presentation is as follows: Husgen 3+2 cycloaddition reaction, limitations of uncatalyzed 3+2 cycloaddition reaction, catalytic 3+2 cycloaddition reaction, interplay between experiment and theory, transition metal catalyzed 3+2 cycloaddition reaction, copper-1 catalyzed 3+2 cycloaddition reaction, conclusions, and acknowledgement. The Husgen 3+2 cycloaddition reaction is the coupling of a 1,3 dipole and a dipole aerophile to yield a 5-membered cyclic compound. The cycloaddition process involves the formation of 2 new sigma bonds at the expense of 2 pi bonds as shown in scheme 1. Professor Husgen was among the first pioneers to understand the scope of this organic reaction. Let's have a look at some of the basic aspects of 3+2 cycloaddition reaction. First of all, the 1,3 dipole is defined as the ABC structure, which can be classified into 2 different types. The first type is the allyl anion, which is bent in shape. Some examples are the familiar atmospheric components, such as ozone and nitrous oxide. The second type is the allynyl anion, which are generally linear in shape. An example is azide, which is an eminent dipole in the field of click chemistry. The 3+2 cycloaddition reaction are useful processes in the industrial, agricultural, pharmacological field, among others. Yet, the uncatalyzed reaction do have some limitations. Firstly, the uncatalyzed reaction is often very slow. Secondly, for the case of methyl azide and propyne, the activation barrier is much higher than the catalyzed one. Thirdly, the reaction is not regioselective, as illustrated in scheme 2. Moreover, in some cases, when a dipole is mixed with a dipole aerophile without any activator, no cycloadduct is formed. An example is illustrated in scheme 3. To overcome those limitations, various strategies can be adopted to activate the 3+2 cycloaddition reactions. Firstly, the use of a self-activating dipole aerophile, such as the propiolates. Secondly, the use of transition metal catalyst, and thirdly, the use of organocatalyst. The reactivity and selectivities are strongly influenced by the catalysis of 3+2 cycloaddition reaction. Due to the enhanced rate of reaction, as well as the distinct regioselectivity of the reaction, studies on catalytic 3+2 cycloaddition reaction mechanisms have been skyrocketing. Indeed, studies on catalytic mechanism of 3+2 cycloaddition reaction are of paramount importance. Firstly, to optimize reaction parameters. Secondly, to develop novel catalytic processes. Thirdly, to locate and characterize competitive catalytic pathways. And last but not least, to enhance the understanding of fundamental reactivity. As follows, the catalytic mechanisms are often dictated by the subtle interplay between the electronic and steric factors, which makes it difficult to explain or interpret observed reactivities. Hence, quantum chemical computations can be useful in complementing the experimental difficulties. It provides a detailed insight into the transition states, intermediates, and competing pathways. There are numerous attention on transition metal catalyzed 3+2 cycloaddition reaction from both synthetic and theoretical point of view. However, we can observe a changing trend from expensive metal catalysts to more readily available and cost-effective transition metals. In particular, there are several studies, be it theoretical or experimental, on the copper-1 catalyzed 3+2 cycloaddition reactions. Moreover, based on these studies, several mechanisms involving copper-1 has been proposed. Among the various postulates, the archetypal click mechanism has received the widest attention. The objective of my study is to compare the click mechanism, as illustrated in scheme 4, with that of a novel copper-1 catalyzed 3+2 cycloaddition mechanism, as illustrated in scheme 5. The B3LYP6-31GD level of theory was used. All computations were conducted in solvent. IRC computations were also performed. Additionally, azomethine A and terminal alkyne B were used as representative substrates to analyze and compare the catalytic cycles. It was found that the transition states connect coherently to the minima on the potential energy surface. Additionally, the novel copper-1 catalyzed 3+2 cycloaddition reaction has a lower energy barrier than that of the click mechanism, and thirdly, the energy barrier of click mechanism is higher than that of the uncatalyzed one. As conclusion, it can be deduced that the click mechanism is not appropriate for the 3+2 cycloaddition reaction of azomethine and terminal alkyne. The novel copper-1 catalyzed mechanistic postulate is well versed for the reaction of azomethine and terminal alkyne. Moreover, this study can further incite experimentalists to isolate and characterize the intermediates. Future work: the substitution effect on the 3+2 cycloaddition reaction of azomethine and terminal alkynes will be studied. I would like to acknowledge Professor Ponadurai Ramasamy, Dr. Lydia Reimann, Professor Luis Domego, Professor Alan Kutritsky, Dr. Alex Oliferenko, the organizing committee of ECSOC, University of Mauritius. Thank you.